If you have multiple resistors that are hooked up in series, one after another, or parallel with each of their sides connected to each other, those resistors can be considered the same as a different size resistor, a single one, an effective resistor. Now, why would you use more than one resistor instead of just using the resistor you need in the first place? Because resistors are not manufactured in every single size. Imagine a 1 ohm, 2 ohm, 3 ohm, 4 ohm, 5 ohm, 6 ohm, 7 ohm, 8 ohm resistor go all the way up to mega ohms. It's obviously not possible. Also, resistors are cheap, especially in bulk. We're talking fractions of cents here, once you get into the bulk of mass-produced things like cell phones. Resistors are cheap, they're also small. So if you can put together multiple resistors to make any value you want, there's no reason to not do it. Perhaps if you have need of one specific value resistor and you are incredibly cramped on space and you're making hundreds of thousands of items, you might commission that specific resistor from some random Chinese factory. But the vast majority of the time, you're just going to put a couple down and hook them together to make whatever value you need. Now, I'm going to show you the equations that allow you to calculate what resistor value you get. And you might be tempted to walk away right there and say, well, there it is. That's all you need to use them, so why listen to me blather on? Well, the purpose of listening to me blather on is because I'm explaining things, not just telling you. If you just wanted to know what the equations were, you would have Googled them. I'm going to show you, using Kirchhoff's voltage and current laws, why they are the way they are. Now, you're not going to use that knowledge in everyday life. In fact, you're not even going to remember it unless you have an eidetic memory. Just like I was talking about the Pythagorean theorem, it is excellent for you to go through the explanation once, to see it, understand it, be confident in it. Because first of all, every time you use the equation, you may not remember any of that proof, but you will remember having experienced it. You will feel more confident, rather than saying, oh, I got this off Google and it seems to work fine. You know, this site looked pretty reputable, or it was in my textbook. You have gone through and said, this is right. I have observed the history of the science of electronics. And while I may not be a professional scientist, I feel like I've peeked over their shoulder a bit. And not only that sense of confidence you get, but also, have you ever heard of something called learning how to learn? Learning is not about memorizing facts. It's not about memorizing how to do algebra and calculus. No matter how complex the things you do are or become, it's not about learning how to do that thing. If you learn how to learn, that is a skill that will last you your entire life. You will be able to pick up random bits of knowledge, wisdom, skill through everyday life that you'll then use 2 years from now and go, well, that was pretty handy. I already know how to do this. It improves your deductive thinking. It improves your inductive thinking. It improves your problem solving, your ability to sift through facts, your ability to look at something quickly to determine whether it seems like it's right, whether it's worth delving more into. But instead of continuing to blather on about me blathering on, let's do some math. Resistors that are placed one after another, end to end, are in series. Your power source, running through the resistors one by one with no junctions. Let's label them V1, V2, V3. We'll say the power is Vp just for fun. If we use Kirchhoff's voltage law, go around one loop, we get this. Vp minus V1 minus V2 minus V3 equals 0. Or Vp equals V1 plus V2 plus V3. Quite intuitive. You have the power here and it gets used up by the things in the circuit. Now how do we use that to find the combined resistance values? Ohm's law, V equals I times R. We have R, we know what the resistors are. R1, R2, R3. And here's what your equivalent resistance is going to be. If you replace these all three together with one resistor, with one end here and one end here, just replace them. R prime equals R1 plus R2 plus R3. If they're in series, you add their ohms and you get the equivalent ohms. Let's actually do that math. So I've just moved this over. Now let's say we had one resistor. Instead of R1, 2, 3, let's say R prime. And its voltage will be V prime. So V power equals V prime. Did the same thing. Kirchhoff's law. V plus and then minus V prime. The one resistor. Just like we have minus, 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 we have one minus. But these are equal. However we end up calculating the resistance values, whatever this math turns out to be, we have said, whatever this is a resistor that's equivalent to these three resistors. It has to be the same voltage. So we can say V prime equals V1 plus V2 plus V3. This is just saying our circuit, our equivalent resistor of these three resistors, drops the same voltage as these three resistors. Obviously, we're trying to say it's the same. Voltage equals current times resistance. The current is going to be the same through all there. The only thing different is the resistors. And you say, well, changing the resistance changes the current. We're saying, what is the resistance that gives us the same current? We're setting the voltage the same, we're setting the current the same, and we're saying, okay, what is the R? That's our unknown, R prime. That's why we're saying the same current. So I times R prime equals I times R1 plus I times R2 plus I times R3. So we're saying these voltages are the same. We're saying it's all the same current. And we know R1, R2, and R3. We don't know R prime. We don't know what this is going to be. We're trying to figure that out. We're not assuming anything. We're saying, mathematics, tell us, please. But we have the current in all these algebraic terms. We can just cancel them. And we get R prime equals R1 plus R2 plus R3. And there it is. Kirchhoff's voltage law has the answer. You may also see this presented with the Greek capital letter sigma of something like R prime equals sum for I of n of Ri. This is just mathematical notation for a sum. It's saying I is 1, 2, 3, n is 3, so I goes from 1 to 2 to 3. R1 plus R2 plus R3. That's just the mathematics way of saying it. So you just add them together in series, and that's your resistance. So now we have resistors in parallel. All of one side of them is connected together. All of the other is connected together. This time we're going to use Kirchhoff's current law instead of his voltage law. Recall that the current law just says, for any junction, the current in must equal the current out. Or if you assign a positive to one of them and a negative to the other, then they add to 0. So let's label the currents. And we'll just do one junction. You can do the math for all of it if you really want. It just comes out the same. Let's say I power, I1, I2, I3. I1, I2, I3 are going into one side of the resistor. I power is going in. Of course, this is going to be the same current on the other side of the resistors. And through each resistor is the same, so it's all the same currents. We only have 4 currents throughout the entire circuit. And Kirchhoff's current law says that IP equals I1 plus I2 plus I3. Recall that we could have done the negatives as well. We could say inward is negative and outward is positive. So we have negative IP plus I1 plus I2 plus I3. Then we just move the IP over and we get the same thing. But then we have Ohm's law again. V equals I times R. So just as a spoiler, what are we going to get? In this case, 1 over R prime equals 1 over R1 plus 1 over R2 plus 1 over R3. It's dividing into 1, it's taking the reciprocal, it's flipping it upside down, whatever you want to say. You take each resistance value, flip it, add them together, flip it again to actually get your R prime. Because if you wanted to just say R prime, you have to take the reciprocal, flip this side, and flip this entire side. But that's a little cumbersome. So let's change Ohm's law to be I equals V over R. We just divided the resistance over. So we can rewrite this and say that I1 plus I2 plus I3 is V1 over R1 plus V2 over R2 plus V3 over R3. And we want to equate it to our other one. So we're saying we want to replace this with an equivalent resistor. One resistor that connects here and gives us the same voltage drop, the same current. What is the resistance that does that? So that means, well, if the current's the same, the current's the same. IP equals I prime, our equivalent one, which equals V prime over R prime. So we can set these equal because we're comparing what gives us the same current. But here's the thing. Without doing the math, because we already did that in another video, the voltage is going to be the same across all these resistors. You can do it with Kirchhoff's voltage law. Do a loop here, a loop here, and a loop here, and you'll see that every single voltage drop is the same. Every single resistor drops the entire voltage. It's the currents that vary. That's why we're using the current law. So we don't have V1, V2, V3, and V prime. We just have V. So over here, the voltages across all three resistors in parallel are the same. And then we're keeping it the same over here. We're saying, with the same current and same voltage, what is our R? That's our unknown. So let's rewrite this. V over R prime equals V over R1 plus V over R2 plus V over R3. Just using Ohm's law and saying, well, all the voltages are the same, but the same thing. We have V multiplied by all of these terms. We can divide V out across the entire thing. Get rid of the V's. My, that looks familiar, doesn't it? This is what happens when you have resistors in parallel. And once again, this is on the bottom, you just have to flip it again. So you take this whole thing, and you flip it, and you get rid of that. It's just a whole lot easier to write it the other way. So let's observe what actually happens here. It's obvious with resistors in series that if you increase any of the resistors, you increase the total resistance, because you're just adding them. If you decrease them, you decrease the total resistance because you're just adding them. But what is going on in this one? Well, pick 3 random values, then change one. Let's say you increase R1. Well, what happens? If you increase the bottom of a fraction, you get a smaller number, see? Because 2 is smaller than 3, but 1/2 is bigger than 1/3. You're dividing 1 into more pieces. So if you increase R1, you are decreasing this piece. And since you have a sum of these pieces, these two are the same, you're just changing this one. So you are adding a smaller value, which makes this sum smaller. But you're dividing by a smaller number. So increase R1, decrease this piece, decrease the whole sum. But now you have another fraction, this piece divided into 1. So you've made this smaller, which means the reciprocal is bigger. So by increasing R1, you do increase the total resistance. But the trick is, the bigger the resistor, the less of an effect it has. You'd think if you have, let's say, 3 resistors in series, whatever their values, and you add a 5 ohm resistor. Let's say you had a 10 kilo ohm and a 1 mega ohm and a 500 ohm, and then you add a 5 ohm. That doesn't change the resistance by very much at all, just a tiny bit. But what if you do it here? What if you add a resistor? What if you add a 10,000 ohm resistor, 10 kilo ohms? Well, you're dividing 1 into that. So you're adding 1/10,000th onto here, which is not changing this sum by very much at all, which means it won't change this by very much at all. But what if you add a 2 ohm resistor? So that becomes 1/2, that becomes 0.5. So if you added a 100 ohm resistor, that would be 0.01 of a change. If you added a 10 ohm resistor, that's a 0.1 change. If you added a 1 ohm resistor, that's a 1 change, a whole 1. If you had half an ohm, you'd be adding 2 down here. But furthermore, if you're adding resistors, if you leave this alone and add a resistor, whatever the value is, it's going to be positive, which is going to increase the sum, which is going to decrease the whole thing. Adding resistors decreases the resistance. You can increase the value of one of the resistors you already have, and that will increase the resistance. But if you add another resistor, you're decreasing it. And then you'd have to make that one bigger and bigger to get back up to it. So this one is much more for fine-tuning. But anyway, let's try this out with some real resistors just to show you I'm right. So I have here 3 resistors in my breadboard. They are supposed to be 5.6 ohms, 18 ohms, and 33 ohms. Let's find out if they really are. 6.2, 18.5, and 33.4. It's all within tolerances. Nothing's perfect in life. You pay more for more exact values. So what happens if we connect them in series? So we connect one, and we connect the other, then we just do our probe between them, and we get a nice big number. Let's do that more slowly. So we have our 5.6 resistor, and then I'll add in the 18 ohm, which takes us up to there, and then I'll add in the third one, and you can see they're just adding plus, 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 and there you go. So let's do parallel. So of course we connect one resistor to shared rails. We'll just go ahead and connect our meter to those rails and leave it there. So we have our first one, which is the 5.6. You'll notice it's different every time because I'm using different wires. There's very slight variances. But tenths of ohms matters not at all in the grand scheme of the universe. So let's add in a second resistor. To the 5.6, we'll add the 18. Watch what happens. 4.8. Say it went down. Let's add another one. Let's add to our 4.8 ohms of resistance, let's add 33. And if I do that, now it's 4.3 again, because 33 is a whole lot bigger than 4.3. 4.2, 4.3, it's a little wiggly. The point is, remember how I said the bigger resistor you add, the less of an impact it has, which is the opposite of series? There you go. But I did say, if you, instead of adding a resistor, you increase the value of one, then it still goes up. So I've got my 5.6 and my 18 connected right now. I'm going to increase the 5.6 to the 33. So it's the same number of resistors, but one of them is becoming greater value. And now we get 12.2. So if you have them in parallel, increase a resistor to increase the resistance, add a resistor to decrease the resistance. So these are the tools you can use to get an exact value. One nice method you can use to figure out what resistance you need is a potentiometer, usually in the form of a trim pot, which is just this without the stick on it, that you turn with a screwdriver instead. You put that in your circuit, and you fine-tune the value until whatever you want to happen is happening the way you want it to happen. Then you just use your multimeter to measure the value coming off of this resistor, this variable resistor, and then use your series and parallel tricks to figure out something that's about the same, using the resistor values that you have. And that's resistors in series and parallel. I hope you can see what I mean about learning the math, about going through the math at least. You'll never retain all of this. You'll have to redo it every time, just like me. Because why would you remember it? That's not useful. Learning is not about memorization. You have a little laminated card or an app on your phone or something that tells you what these equations are, and you just look at that anytime you need it. And if you do it enough, you'll remember it. We tend to remember the things that we use most often. But having this in your brain is not useful beyond the speed of getting to it. If you remember it, you don't have to look at your index card. Whoop-de-doo. The point is you understand it. When you use these equations, maybe something goes wrong, but you understand what's going on in these equations, so you can better figure out what's going wrong. What mistake did you make? What is wrong on your spec sheet? It makes it easier to figure out errors. It makes it easier to spot errors. Think about all the things in life that have gone wrong just because not everyone tried their best, like the Hubble Space Telescope. The Hubble Space Telescope had a rather disastrous failure in its early days. You can look it up on Wikipedia. But suffice it to say, there was a chain of people, and each of them made a mistake, because they weren't really trying their absolute best. Now, everybody makes mistakes sometimes, but the point is, if you are trying very hard to not make them, the chance of you making one is low. And the chance of you and the next guy who's also trying very hard is even lower. Sort of like a sum of reciprocals. If everyone tries their very best, if everyone's looking for mistakes, then it makes it much more likely that only one person will make the mistake and 3 other people will catch it. Somewhere down the line it will be caught and fixed, instead of constructing an extremely expensive telescope that doesn't work right. You don't need to memorize, you need to understand. And I hope you'll stick with me as we both increase our understanding as time goes on. But for now, be seeing you.